Hello everyone. Alright, 9.4, and it's my last video before I get on a plane to go to Rome. So excited. Okay, so there we go. We're going to talk about 9.4, which is thermodynamic and kinetic control. This is a super short section. So we've talked about delta G is thermodynamically favored, and if delta G, well, it tells us our thermodynamic favorability. And then if delta G is negative, then it's favorable to be spontaneous, and then which means it just sort of happens on its own. And then if it's positive, then it's not. Well, sometimes there are, of course, situations that kinetics can somewhat control how a reaction goes forward. So we'll talk about it briefly. AP doesn't get into this incredibly in depth, but we're just going to kind of touch the surface of this. So we have this equation that we've already talked about, calculating delta G, and most of the time, if you're calculating delta G in AP Chem, this is the equation that you typically use. On the last 9.3 section, there was a problem where you had the delta G table of values. You could have that, but typically they use this equation. It's the more popular one for them to use because they like the problems that go step by step. So you'll have delta S from one part, and you go get delta H in another part, plug them in together and predict spontaneity. That tends to be the norm. So we talk about reactions where their delta G value is negative or less than 0. We predict that that is a spontaneous reaction. Now, if we take a look at whether or not a reaction occurs, we have the kinetics. So this is a great energy diagram, and yes, we call this delta H, but you can also overlap that with delta G. But the point is that it's favorability. So exothermic reactions tend to be favorable. It gives us a favorable delta H, and considering or depending on what the species are and the reactants on the product side, we will have a delta G value that's negative many times. So what we have is this part of the bottom part from the products to the reactants represent the thermodynamic part of the equation. But then there's this upper part, right? And we know about this from kinetics. This is our activation energy, and that's how fast will it occur. And we've talked about back in the day when we did kinetics, we talked about how it's got to be, the molecules have to have the right speed and the proper orientation, and all of these things have to occur. And remember, we talked about unimolecular and bimolecular and termolecular, and how termolecular very rarely happens. That's 3 or more molecules that have to collide at the same time. Can they happen? Yes. Do they happen super fast and very often? And the answer is typically not. They usually do need a little bit of help. So what we talk about when we're looking at this equation or what's going on is understand that there's a couple of different factors that have to align for a reaction to go completely in a totally favorable format to where we could have a negative delta G. So it says, oh, it's thermodynamically favored, it's going to happen. But then it could happen not that often under those circumstances, or there could be some type of kinetic control that's slowing this reaction down. So it depends on what's happening up here. Will also depend on if we actually see the results of this reaction being thermodynamically favored. Okay, so it can be limited by the kinetics of what's happening, and so that's what we're going to talk about briefly. So spontaneous reactions that don't occur. They're not very common, but there are some, and there's one that's pretty popular that we'll talk about in just a second. Although I've never seen them ask this on the AP exam, but we're still going to talk about it. They do talk about this reaction though, so that's why I think it's important. So generally, if thermodynamics predict that the reaction is going to take place, but the reaction does not take place naturally, then we assume that there's some kind of kinetic control. There's something happening in that upper part, up where the activation energy is. Something is going on there. And so it could be a really high activation energy, unfavorable orientation, so crazy looking molecules of the way that they have to come in and collide, and then the number of particles that must collide simultaneously. So something's happening up in that hump right? Where the activation energy is. Something's going on that's preventing this reaction from happening because it should be happening. So go forward. There we go. So this is the perfect example. So this is called the Haber process. And again, I'm barely touching on this. This is our last slide. There's not a lot to this unit or to this section because typically in AP, they kind of stop with if delta G is negative, the reaction goes. But of course, this is chemistry, so I've taught you that there's exceptions to everything. But this is the Haber process. So consider the reaction represented above at 298 Kelvin. Please recognize 298 Kelvin is room temperature. It's 25 degrees Celsius. So when equal volumes of N2 and H2, each at 1 atmosphere pressure, are mixed in a closed container at 298 Kelvin, we don't really observe a lot of NH3 being formed. It is exothermic, so that's favorable. Delta G is also negative, that's favorable. So look at what they give you. So check, favorability is big. Take a look at this. I mean, this is pretty, this is a pretty low or negative delta G value. So that's good. Now you could look at the delta S, which they don't give you. We don't have a numerical value for it, but with having H and G in the temperature, we could calculate it. But you could see this and go, well, there's 4 moles of gas turning into 2 moles of gas. So that's more orderly. So in this case, you could predict that the S value is also negative. All right. So think about that and what's going on in those circumstances. Now, it says, consider this reaction. So which of the following best explains this observation? So let's look at what they gave us. It's a negative delta G. It should be thermodynamically spontaneous. It should happen on its own. Doesn't mean it's going to happen fast. So we don't really observe a lot of NH3 being produced. So they give us this multiple choice question, and let's run through it. It says the N2 and the H2 must be mixed in ratios of 1:3 for the reaction to occur. No, they don't need to be mixed in 1:3. That's the multiple ratios in which they will react, but they don't have to be mixed in those ratios, so no. B, a high activation energy makes the forward reaction extremely slow at 298 Kelvin. Okay, that sounds pretty darn good to me, but I'm going to see what the others say real quick. C, the reaction has an extremely small equilibrium constant, thus almost no product will form. No. All right, D, the reverse reaction has a lower activation energy than the forward reaction, so the forward reaction does not occur. No. Okay, no to C and D. So this is the Haber process. And believe it or not, you would think making ammonia would not be that complicated, but it's hard. And so in order for this to happen, it is spontaneous in the sense that the delta G is negative, but in order for this to happen, typically in a laboratory setting, they will crank the heat up because it's, that's just what they do. They tend to change the temperature, they change the pressure, they increase the pressure a lot. And you're like, but why? Well, take a look at what's going on and what you're breaking apart. I have H2, that's a hydrogen-hydrogen single bond. But then I have N2. That's 2 nitrogens nitrogen is a pretty small atom, and they're triple bonded together. So in order to bust and break apart triple bonds, I gotta have a lot of energy. And so the collisions are the issue. So they're not gonna ask you on AP to really postulate why this is the case, okay? But I'm just explaining it for those that wanna know that nitrogen's triple bond is causing the problem because it's really, really, really a tough bond to break apart. So it has answer B, has a really high activation energy, making the forward reaction extremely slow would be the correct answer. And the reason why is because the amount of energy that hydrogen needs in order to slam into this nitrogen, in order to break it apart, because that nitrogen has triple bonds, is going to be really, really, really high. So that's why this tends to not produce a lot of ammonia just sitting at room temperature. It doesn't mean that it won't produce some, but it's just going to need a little bit of help. But the issue is kinetics. The issue is not thermodynamics. So the issue with this reaction is a kinetic control, not a thermodynamics issue. So thermodynamics, it's set up pretty much perfectly. There is a little bit with the delta S, but it's set up pretty perfectly with the delta H and delta G is negative. So that's the ultimate deciding factor. but it has to do with the N2 molecules mostly because of that triple bond. All right, I think that's our last slide. That was easy, right? So 9.4 isn't super heavy on the AP exam because, like I said, they tend to just take you through this equation here, what we did in 9.3. This is where you're going to spend most of your time on delta G on the AP exam. But in the event that they asked you something about kinetic control or something odd like this special case, then you've at least been exposed to it. And the last thing I will tell you, and I have kids do this, or students do this to this day. Oh, sorry, my foot fell asleep. If they give you any problem or equation like this, now this one's multiple choice, but if it's on a short answer or a free response, I have so many students that'll come up and say they are given this information, but then they're told, is not observed. And the students go, oh no, false. Delta G is negative, it's gonna go. Okay, listen, if the AP exam tells you that something doesn't work, then look at the prompt carefully. Don't try to disprove them unless they tell you to disprove them, but that's not typically the case. They're telling you the truth, and they're trying to see if you can pick out why. They're trying to see what you know in terms of explaining the exception, because there's tons of exceptions in chemistry. So never try to disprove anything that they say. Don't tell them that they're wrong, because they're not. They are 100% correct in whatever they tell you. The only time they ask you to disprove something is if they talk about a student. A student said this. Do you agree or disagree? Okay, that's different. But if they give you this information, don't just go, oh, delta G is negative, so it's going to go, the statement's false. No. Delta G is negative, thermodynamically favored, yes. It's thermodynamically spontaneous, yes. But there's other factors. So in this case, that's where we're talking about kinetic control. There's something going on here that's causing problems. Okay? So just so you know, it's not something that they ask a lot. They really don't. I very rarely see it, but I just wanted to do this with you real quick. All right, that's it. Super fast. I could have just combined it with 9.3, but I didn't. All right, guys, I will see you later. Bye.